Here's a really nice number theory problem from the 2025 Indian Mathematical Olympiad. The integers 1, 2 to n are written on a board. In a move, Alice can pick two integers from the board where a is not equal to b and a plus b is even, erase a plus b and replace them with a plus b on 2. Find all n 2 or greater for which Alice can make a sequence of moves to leave only one number on the board. Note when n is 3, Alice changes 1, 2, 3 to 2, 2 and cannot make any further moves. What I love about this problem is it's such a simple idea. We're just choosing any two numbers, replacing them by the average. The goal is to get to one number remaining on the board. So n equals 7 can be done, and one way of doing that is shown here. We're already told that n equals 3 cannot be done. So a logical place to start would be to try n is equal to 4. If you try n equals 4, there's only two choices for the first move. Either you replace 2 and 4 with 3, or you replace 1 and 3 with 2. In both of those cases, that you're then forced into a second move, and both cases you end up with 2, 3, and you can't make any further moves, you're stuck. N equals 5 can be done. You can try it yourself if you like. For n equals 6, you can try it yourself if you like. After a few tries, you probably get the sense that it's probably not possible. I haven't listed all the options here, but you can pretty much list out all the options. There is also a clever proof, which I'll show at the end, to prove that n equals 6 is actually not possible. Given n equals 4 didn't work, n equals 6 doesn't seem to work, but n equals 5 and 7 do. My thinking at this stage was probably all odd n were solutions. And the way I tried to prove this was to turn the problem around and to start with a single integer and remove it and replace it with two surrounding integers, until we can try to get a sequence of consecutive integers in the end. I used a series of dots on a grid like this to save time writing integers, and also so I didn't have to know exactly where to start. So long as I can get to a sequence of consecutive dots, then I can get to a sequence of consecutive integers, and also go in reverse. So here is a solution for n equals 7. And investigating the dots on the grid like this, I actually quite enjoyed that, and it reminded me of something I read in one of my favorite old books. But anyway, I was able to generalize this strategy for n equals 5 and n equals 7 to work for other odd numbers. And the way I did it was to use the same two initial steps every time. Then in the third step, take that middle dot and move k steps to the right and left. So using k equals 3, for example, I get to 9 consecutive integers. Using k equals 4, I can get to 11 consecutive integers. And I can see it's always going to work because after that third step, where I have 4 dots, I'm always getting 2 blocks with a similar structure like this. Each block has a number in the second place from the left and a number in the second place from the right. And I can fill each of those blocks just by starting from left to right, and each time replacing an integer by the one directly above and below. So for any k, I can end up with a block of k plus 1 and a block of k plus 2, giving 2k plus 3 consecutive integers, which will be able to give all odd integers greater than 5 and 7, which I'd already done. I didn't realize until after reading the solutions that there's actually several easier methods for generating all odd numbers. And one of them is actually staring me in the face as I look at that diagram. But anyway, I'll come back to more elegant solutions at the end. In my process, I couldn't find a way to generalize that strategy to work for even numbers, but just by playing around, I was able to find solutions for n equals 8 and n equals 10. So by this stage, I'm thinking actually it probably is possible to get all high even numbers. One way I found to get all multiples of 4 was to use 2 of the odd numbers next to each other by splitting the first integer into 2 that are like at least 5 apart. So for example, I can get n equals 12 by making a block of 5 and a block of 7. But I couldn't get 14 because that central integer would need to be like 3.5 apart from the 2 integers. So that wouldn't work. But n equals 16, I can get a 7 plus 9, and any multiple of 4, any higher multiple of 4, I could get that way. So the only numbers left were the 2 mod 4, like 14, 18, 22, etc. At some stage, I realized I could get the 2 mod 4 numbers by using a block of 10 and adding a block of 10 to the multiples of 4. So for example, here 10 plus 12 gives 22. So by this time, I was pretty confident with the actual answer to the problem, but my solution seemed like too complicated, and I felt there should be something more elegant and more direct that I was missing. So I looked up the solutions and what I found was pretty interesting. Here's a post by the problem creator, Rohan Goyal, where he explains that even though he created the problem, actually even he did not find an elegant solution, but his colleague was able to find one. So here's how it works. The idea is to start by replacing n-1 and n-3 with n-2, and then work down one step at a time until there's only 3 numbers remaining, which are 2, n-2, and n. In the odd case, we replace n-2 and n with n-1, which is even. So 2 and n-1 can be removed and replaced with a single integer. But the really clever part is the even case. In that case, exactly one of n-2 and n must be divisible by 4, and one must not be. The one that's not can be removed with 2 to leave an even integer. So in this example, 2 and 10 are removed to leave 6. 6 is even, so is 8. So then we can remove it and leave a single even integer. So that's quite clever, and yeah, I couldn't really think of that. For the odd case, I really should have seen a simpler way to do that. Like I had 2 blocks, but I could have just used a single block. For the even case, probably my method of working backwards didn't really help me because it's a bit hard to think of those first few steps. This is how it would look for n equals 14, for example. For n equals 6, the official solutions had a clever mod 3 argument. So the numbers from 1 to 6 contain 2 numbers that are each 0, 1, or 2 remainder 3. If we list them in a table like this, what happens every move is that 2 numbers need to be chosen from different mod 3 residue classes. And the number that's added is going to be from the third class. So in each step, 2 of the columns go down by 1 and the other column goes up by 1. Because we start from 2, 2, 2, that means that in each step, all the columns are either going to be all even or they're going to be all odd. Therefore, it's not possible to end with 0, 0, 1 and leave only one number remaining on the board. So that's all. Really nice problem and a clever solution.
1, 9, 4, and a 5. Right. 5 and a 7. Oh, right. 5 and 7 is a 6. So 2 6s. 1 7.
Why are you under the table?
6 and...
Because I need to get stuff.
Hold on.
They're big
Got it,
brain.
Cross out 6 and 8.